Namaskar, Fundamentals of Physics, my third lecture and part 2 of Kinematics in One Dimension. In this lecture, we will talk about length as a physical quantity. I begin my presentation with a quotation from Saint Isidore: "Take from all things their number, and all shall perish." In physical quantities, the values are assigned, the numbers are assigned, and these numbers are very, very important, not only in knowing about the state of the system, but also in understanding kinematics or dynamics of the system. In our previous talk, I have explained the concept of Newtonian particle, a hypothetical system, which is our current focus of study, and to understand or develop a theoretical framework for describing kinematics of particle in one dimension, we must know certain branches of mathematics. These branches of mathematics were pointed out in my last talk: Euclidean geometry, the number system, especially real numbers, because real numbers are more important in physics, algebra, real number algebra, coordinate geometry, and the real Euclidean space. These concepts, the concepts in these branches are very, very important, and these branches were pointed out in the last presentation. Now we recollect that in physics we study physical systems. Physical systems have physical characteristics. More often we are interested in those characteristics which can be measured in experiment or which can be expressed quantitatively. Quantitative physical characteristics are called physical quantities. These physical quantities we will be defining in our due course. Today we will discuss as an example length as the first physical quantity. However, in my previous talk I have mentioned that mass of the particle is an intrinsic property, and that is also a physical quantity. But detailed discussion about the mass, its unit and dimension will be taken up in the next lecture. So to understand length as a dimension and what are units of length, how length is expressed in physical theory, we have to recollect that in previous discussion I have pointed out that a physical quantity, there is an associated number or value, an associated unit, and it has some dimensions which we will be defining, and it has tensorial character, and also it becomes important because a few physical quantities can be specified without any reference to a frame of reference. So those quantities are called absolute, and few quantities, other quantities in fact not few, which can be specified in reference to a frame of reference are called relative. Length is a physical quantity, and length has a dimension of length, but there are many synonyms of length which also have importance: height, width, breadth, perimeter, circumference. All these quantities have dimensions of length. Suppose someone asks you what is your height, you will specify it. My answer will be that my height is 170 centimeter. 170 centimeter is the value of my height, a physical quantity, and 170 is the number associated with it, and centimeter is the unit associated with it. Dimension definitely of height is that of length. So my height is 170 centimeter, communicates to you that it has a value 170, it has a unit centimeter, and it also has a dimension of length. But there are many unit systems. So instead of saying that my height is 170 centimeter, I can make a statement that my height is nearly 5 feet 7 inches, and which I can write as 5 single prime 7 double prime, or 5 ft 7 in. So ft is the symbol for feet and in is the symbol for inch. And similarly, single prime is used as symbol for feet and double prime is used for symbol for inch. So the quantity like height, length of objects were known to us right from the civilization long back, even before Bronze Age. Archaeologists believe that Egyptian, ancient Indians and Mesopotamians were using a unit called cubit. Cubit is shown in the picture. It is defined by this. The definition of cubit is clear to you from the picture above my image. And the cubits were common in those cultures, but Romans and Greeks were using another unit of length, and that is called foot. In Harappan civilization also, a different foot appears in the archaeological studies, and that too corresponding to Bronze Age. Why I am pointing out this thing here? If we go through historical facts and we use the traditional values of the unit of length, it will not be convenient to us in scientific deliberations and discussions. There are many unit systems. So slowly the scientific community has realized the importance of agreeing to some standard unit system, and that standard unit system, you may already be knowing, is called SI unit system. Before SI unit systems, many unit systems were commonly used by scientists in their literature, in their papers and deliberations. Centimeter gram second, foot pounder second, foot pound second, meter kilogram second. These were common unit systems used in earlier days. But now, since 1960, the scientific community is using what is called International System of Unit, which is on the basis of its French name, is abbreviated as SI units. So SI units we will be using in assigning physical quantities the values and unit and as well as dimension as far as possible in our deliberation. We will stick to SI unit. Now the unit systems are evolving systems. Like biological systems are evolving, the unit systems are also evolving, and very recently in 2019 the international community has agreed to define all these 7 base SI unit in terms of the physical constants, the constants which can be precisely measured in experiments and which are very important also in deliberations of the experiment. So we use this physical constants, defining constants, to define these 7 base units which have been identified. Before that, in 2009, we have agreed to what is called International System of Quantities for how to specify physical quantities. The entire agreement is there. It is based on a concept called base quantity. So out of the possible set of physical quantities, it would be a very large set, and as we move forward in our course, then we will be noticing that day by day after every lecture or few lectures we introduce new quantities. So how many physical quantities have been defined? It's not infinite definitely, but it's a large number. Out of that large number of set of physical quantities, they have chosen 7 quantities as base quantities. These quantities do not depend upon each other, so they are mutually exclusive. For example, one of the base unit is length, and length is a base quantity, and the other base quantity is mass. So length and mass do not depend upon each other, and at least this is true in the theory which we will be discussing in few lectures from now, so in classical physics. The idea, the unit system, SI unit system, is not a favored unit system in discussions in high energy physics, and we use a different unit system called natural unit system. That will be discussed later only. So we remain interested to the Newtonian mechanics only for time being, and there the idea will work very well that certain base quantities can be selected, and the community has selected 7 base quantities, and these 7 base quantities are therefore very important, and you must have a clear understanding of these 7 base quantities, because all other quantities, their dimensions and their units will be expressed by using these base quantities. So in terms of these base quantities, so if you are not familiar with the 7 base quantities, you will not be able to understand the physical quantities which we will be introducing later in the course. And in the international system of units has provided a coherent system of units of measurement for each of these 7 base units. And in this slide I have given a table in which we have listed base quantity, quantity symbol, symbol for dimension, SI base unit, and SI unit symbol. So for example, length is a base quantity agreed by ISQ. Its quantity symbol is italic L. Its symbol for dimension is capital L. Its base unit is meter, and the symbol for the base unit is small m. And similarly, for the mass, the quantity symbol is italics M, the symbol for dimension is capital M, the SI base unit is kilogram, and the symbol for SI base unit is kg in small kg, small k, small g. Time is another base quantity. Its symbol, quantity symbol is italics T, its symbol for dimension is capital T, its SI base unit is second, and its SI unit symbol is small s. And at least for coming few lectures, you would have to remember these 3 base quantities, length, mass and time, because many quantities which I will be introducing in coming lectures will be involving dimensions of length, mass and time only. But later we will move further and discuss electricity and magnetism and electromagnetism, and then the electric current, the 4th quantity, would also become important, and base quantity. Electric current, quantity symbol is I, italic, and the symbol for dimension is capital A, the unit is ampere, and SI unit symbol is capital A. Thermodynamic temperature would also become very important when we take up thermodynamics, and for that quantity symbol is italic T. Now you have to be very cautious. You just find that quantity symbol for thermodynamic temperature is italic capital T, and the symbol for dimension of time is capital T. So you have to be cautious. Symbol for dimension of thermodynamic temperature is capital theta, a Greek character, and the SI base unit for temperature is Kelvin, and which is represented by the symbol capital K. Capital K will not be used for kg. Remember, in kg the K is small. The capital K is SI unit symbol for the temperature, thermodynamic temperature, which we will define in thermodynamics based on zeroth law of thermodynamics. Amount of substance again would become very important in thermodynamics, and that quantity is expressed by the quantity symbol small italic n, and the symbol for dimension is capital N. The SI base unit is mole and it is written as MOL. And luminous intensity would also become important and later on, and the quantity symbol is italic capital I subscript V, and the symbol for dimension is capital J. The unit is candela and the SI unit symbols is CD. So whenever a new quantity will be defined, its quantity will be expressed in terms of these base units. Now, to concentrate or to focus on the length. Length is a physical quantity which has dimension of length, and for which the SI unit which has been assigned is called meter. So meter is the SI unit of the length, and as noticed earlier that the small m is the unit symbol. Now initially the definition of meter was given in terms of the distance between the pole of the earth and the equator, and that distance between the pole of earth and equator was assumed to be 10,000 kilometer, and based on that one can define 1 meter. But this particular definition, which was the first standard definition for a standard of length unit, and that is a standard meter, this was not suitable because this distance between pole and equator, it's difficult to measure accurately and precisely. So for practical reason, the earth standard was abandoned and a new definition of the meter was introduced. And that new definition is not the current definition, but it was a new definition at that time, and the meter was defined as the distance between two fine lines engraved near the ends of a platinum iridium bar and the standard meter bar, which is kept at the International Bureaus of Weights and Measure office near Paris, and the length of a solid depends upon the temperature, and therefore it was specified that the length should be measured at 0 degrees Celsius. So we can say 1 meter is the distance between those two lines engraved on the meter bar at 0 degrees Celsius, and then copies of this standard were made and were distributed to the laboratories worldwide, and so from those we can generate and make new copies and so on. So the definition of meter, second definition of meter, was in terms of the distance between two lines engraved on a platinum iridium bar. But this was also discarded, and in 1960 we came to a new definition. This new definition is based on a natural phenomenon, and this definition is very much practical because it is very easy to set up an experiment and calibrate a meter by using this particular definition. In 1960, the new standard of meter was defined on the basis of the orange-red light emitted by atoms of krypton-86 in a gas discharge tube. So the atoms of krypton-86 in a gas discharge tube emits orange-red light, a particular orange-red light which we can identify, and 1 meter was defined as 1650763.73 wavelengths of the particular orange-red light. Now you will get surprised that why such an awkward number. Such an awkward number was chosen so that the new definition, which is based on krypton-86 orange-red light emission, should match or should be as close as possible to the old definition, which was based on two lines engraved on platinum iridium bar and the distance between those two lines measured at 0 degree Celsius. Later, this definition in 1983 was again discarded, and the current definition, and as I have pointed out earlier also in the beginning of this talk today, that nowadays in SI unit systems we have definition of all the base units based on physical constant, the fundamental physical constants. One of the fundamental physical constant is the speed of light in vacuum. Remember, speed of light in vacuum is different than the speed of light in say water or in any other medium like glass, or speed of light is a quantity which can be physical quantity which can be measured very precisely in experiments, and that is why we have based our new or current definition of the standard of meter on the speed of light, and we choose speed of light with this new definition of meter. Then the speed of light will be equal to 299,792,458 meter per second. Maybe you will like to read it like 2.99792,458 into 10 raised to power 8 meter per second. However, in many approximate calculation, we will use the speed of light as 3 into 10 raised to power 8 meter per second. But the correct or accurate value of the speed of light with this new definition, standard definition of meter, is 299,792,458 meter per second, and that has been accepted as the definition of a meter in our SI unit system. And SI unit system is evolving, as I have pointed out, and the units of not only the base unit of the length but the base units have also evolved for other base units have also evolved. And the base units, I have already pointed out, are very important, because in terms of these base units, the units of other quantities are assigned and based on the dimensions of those quantities, and we will be learning about that in due course. But nobody can restrict anyone not to write the values in other conventional unit system. So as you have noticed that when question was asked to me, I have pointed out earlier that my height is 170 centimeter. Centimeter is a unit in CGS system but not in this SI unit system. But 1 inch, for example, is a conventional unit system. 1 inch you can convert into meter, and for conversion formulas nowadays you can use calculators available on web, so and convert a quantity into from one unit system to another unit system. But it is better that you remember these relations which help you in converting the conventional units into SI units, or one conventional unit into another conventional unit, and it is sometimes required, especially in doing numerical calculations, and in some cases, as I will point out later, wherever it is essential, that formula which we are using may be dependent on unit system, and it will have a different form slightly, or measure different form in different unit system. Like especially in electrodynamics, you will find that the Maxwell equations in CGS system and Maxwell equation in MK systems look different on piece of paper. So these conversion relations are very important. 1 inch is 25.4 millimeter, 1 foot is 12 inch, 1 yard is 3 feet, 1 mile is 1760 yards, and you can convert it into meter also. 1 nautical mile is different than the 1 mile. 1 angstrom is 10 raised to power minus 10 meter and or 0.1 nanometer. 1 Fermi is 10 raised to power minus 15 meter. And for astronomical distances, we use units of length like light year, parsec, and astronomical unit. So you must learn these formulas, you should memorize, and maybe you will be automatically remembering these formulas if you make a frequent use of this formula in solving numerical problems associated with our physics course, and we will have to do that in due course. Now, as an example I am giving here, that you may have, everybody knows about AAA battery. AAA batteries are commonly available in market, and there are measuring instruments. The simplest measuring instrument is a meter scale or scale, 1 foot scale, pit scale, or the scale which is available, 6-inch scale available with compass which you get in India. Then these can be used to measure the length of a one-dimensional object, and there are instruments like vernier calipers and screw gauge. We will discuss the process of measurement and the concepts associated with the course of measurement, like the precision of measurement, the accuracy in the measurement, error in measurement, and the significant figures. We will be taking up that after a few lectures. And for example, to get acquaint yourself with the measurement of length as well as with the idea how the lengths are specified, you can use this AAA battery in experiment. The all AAA batteries are of standard size and dimensions. So are AA batteries and other batteries. So they have fixed or standard dimensions. You can Google and search the dimensions of these batteries, and these dimensions can then be experimentally checked. For example, the diameter of a AAA battery is 10.5 millimeter, and the length is 44.5 millimeters. So every battery will have this diameter and this length, AAA battery, and their quantities may have different name but may be having same dimensions. So as far as the value and the the SI unit is concerned, that will remain same. So literally the terms like height, width, breadth, length, perimeter, circumference, length of a line segment, length of a curve segment, these are different physical quantities, but they all have same dimension of length, and therefore they say all these quantities in SI unit system shall be expressed by using meter as the standard of unit. Now to make, because certain objects we have to cover a large range from the size of the universe to very very small things, and so we have to select certain prefix, and those prefix have been selected by SI units, and these are standard prefix, and you must apprise yourselves about this standard prefix and get acquainted with them, because many times you will find in books and questions and literature that these are used. So for example, for a factor of 10 raised to power 24, the prefix is iota and the symbol is capital Y. And the size of the universe, if you wish to express, then you will have to use capital Y, iota. I will come to that. A value is given in one of the slides which will come up. And 10 raised to power 21 is similarly zeta or Z. 10 raised to power 18 is exa. 10 raised to power 15 is peta. 10 raised to power 12 is tera and symbol is capital T. 10 raised to power 9 is giga and symbol is capital G. And 10 raised to power 6 is mega and symbol is capital M. 10 raised to power 3 is kilo and the symbol is K, small k. And there are other units also like 10 raised to power 2 hecto and 10 raised to power 1 deca, but we will be not using hecto and deca frequently, but milli, mega, giga, tera, peta, exa, zeta and iota would be used in our discussion in this video lecture series. So you must apprise yourself about these symbols and for what value of 10 raised to power what positive power these capital symbols which I have given here except the small k and the letter ones H and DA. So what they mean, that should be on that you should be able to easily recollect as and when required. Now to make you realize the importance, I am giving few examples of the SI prefix. That Google nowadays process large amount of data, and Google processes 20 petabytes data per day. So if you have to express how much data Google processes per day, the SI prefix peta is useful, and peta, as I have pointed out earlier, stands for 10 raised to power 15. The solid state storage devices which are common and which are now being used with computers and laptops. These devices come now even in terabytes. So 1 terabyte, 2 terabyte, and 8 terabyte. To my knowledge, 8 terabyte is the latest storage capacity available for Apple Mac, which I am using here for recording my lectures. And the processor speeds are specified in gigahertz and megahertz. So giga is important, tera is important in SSD drive storage capacity, the beta is important in the amount of data processed by the Google per day, and similarly the other quantities like mega. So maybe you will find that megawatt is the electrical power generation is expressed in megawatts and gigawatt, and kilometer. So kilometer is used as a kilometer. So kilo prefix is used for expressing distance between say two cities, Jaipur and Delhi. So these are very very important SI prefixes, and this use of SI prefixes is shown here, that my height can be written as 1.70 meter, which is of the order of the meters, but the values which are much more than 1 meter can also be expressed by using the SI prefix. So for example, height of Mount Everest is 8.848 kilometer, and the circumference of LHC, the Large Hadron Collider experiment, the most important experiment which has taken place recently, is 27 kilometer. And if we measure the Great Wall of China, then it is in megameter, and so is the distance between Earth and Moon distance is 384.4 megameter, or you can convert that into kilometers also if you so wish. So other higher distances like diameter of the sun-earth distance. Sun-earth distance is very important in physics, and it is used with parallax to measure the astronomical distances, and sun-earth distance, which is 150 gigameter, is also used as an astronomical unit. And orbital distance from Pluto to Sun, the total length of DNA molecule, you will be surprised to know that the total length of DNA molecule in our body, if we can arrange it in a linear manner after taking out DNA molecule from the entire body, then it will be very very large number, 200 terameter, 200 into 10 raised to power 12 meter. And as I pointed out earlier also, that the size of the universe, which can be expressed in terms of say, the distance, co-moving distance of Earth and the age of the universe, between the Earth and the age of the universe, it is 440 yottameter. So very big value, 440 into 10 raised to power 24 meter, the biggest. So as we have SI prefix for a factor greater than 1, so we also have SI prefix for fractions, and those also are very important and therefore should be memorized. And more important, for example, for length is that commonly centimeter is used, and 10 raised to power minus 2 meter is called centimeter. 10 raised to power minus 1 meter is called decimeter. 10 raised to power minus 3, this prefix is milli and the symbol is small m. For 10 raised to power minus 6, the prefix is micro and the symbol is Greek character mu, small. 10 raised to power minus 9, the prefix is nano and the symbol is small n. 10 raised to power minus 12, pico, and the symbol is small p. So you may have noticed some similarity here, that 10 raised to power minus 12, the symbol is, prefix is pico and symbol is small p, and 10 raised to power plus 12, the symbol is what? The symbol is not peta, so don't get confused. P means peta. The symbol is 10 raised to power plus 12 is tera. So, and 10 raised to power minus 12 is pico, and the symbol is small p for pico, and for tera it is capital T. And similarly 10 raised to power minus 15 femto, 10 raised to power minus 18 atto, 10 raised to power minus 21 japto, 10 raised to power minus 24 yocto. These SI prefix of frictions are also very important. Nowadays we have lasers which have time period of femtosecond, and these femtosecond lasers are very useful in treatment and eye cataract surgery, in eye treatment, LASIK surgery of eye, and are being frequently used. Maybe you can find a center in your own town. Nanotechnology is the buzzword nowadays, and nanotechnology refers to research and innovation at nanoscale. And nanoscale means 10 to the power minus 9 meter scale. And 10 to the power minus 9 meter is just 10 times the size of an hydrogen atom. So genetic engineering works at nanoscale. So a mutation of COVID virus is happening, it is happening at nanoscale. But that's a natural nano engineering, and now we have major breakthroughs coming out of nanotechnological progresses. A lot of research is going on in this area, and that's very important, and maybe you will be able to understand all that ongoing research only when you go through a good course in physics. Microprocessors, which you are familiar with and are used in computers, laptops and mobile phones, these microprocessors are called microprocessor because to make this microprocessor, very large scale integration is done, and the doping is done at micron level. So the controlled doping is the controlled infusion of impurities, and so that doping is done at micron level, so the name microprocessor. And vaccines which are being administered for COVID, the vaccine dosage can be expressed in milliliter. Here I have used milliliter. Liter is not an SI unit, liter but is a unit of volume, and milli you can use, so 10 to the power minus 3 liter. Liter you are quite familiar with, so I don't need to say much more, but milliliter is a small quantity and the vaccine doses are in milliliter. Similarly, like in many medicine, the compound is in milligram or microgram value. So to give you an idea about the distances which are less than nanometer, several distances which are less than nanometer are mentioned in this particular slide. Some of these things maybe you will not be able to appreciate at project, like how we arrive at the notion of approximate proton radius. But Compton wavelength, maybe after few tens of lectures, we will be coming to that. Compton wavelength of electron, and that is 2.43 picometer. So picometer is useful in physics because Compton wavelength is assigned by using pico's SI prefix 2.43 value. So 2.43 small p small m is the value of Compton wavelength of electron. Now Bohr radius, you will definitely will come to that. The thickness of the graphene, the nanotechnology has advancement. This new material has been synthesized called graphene. A single layer graphene, the thickness is of the order of 340 picometer. Width of glucose molecule is 700 picometer. Diameter of tobacco mosaic virus is 18 nanometer. Diameter of coronavirus is in the range 65 to 125 nanometer, very small. Nanometer is very small, as you know. Diameter of HIV virus is of the same order. The bacteria are slightly bigger than the virus, and the diameter of a typical mycoplasma bacterium is of 200 nanometer. And the wavelength of light, somebody will say 300 to 700 or 400 to 800 or 300 to 800 or 400 to 800. So that depends upon how you choose and interpret it, but the range are definitely in hundreds of nanometer. Now the next example which I am giving is that the diameter of water droplet in mist or fog or cloud is of the order of 10 micron. Width of silk fiber is of the order of 10 to 50 micron. Width of a strand of human hair is also very fine and 17 to 180 micron. And thickness of the central area of human cornea is 560 micron, and the thickness of credit card is 760 micron. The resolution of human eye is 0.1 millimeter, and therefore all these 20 examples which I have given except the last three, you can say the strand of human hair, silk fibers, the last 4 or 5 on this particular slide, we cannot see through our eye or our vision capacity is limited, and we will come to the concept of resolution of an instrument as well as resolution of eye later on. Now, to assign the value, so you can write the value of a physical quantity as given in these examples in terms of by using a value, then using SI prefix and using SI unit. But another way of which is very common in nowadays in scientific practice is to write the values of physical quantities using scientific notation. In scientific notation, every physical quantity, the value or number will be expressed in terms of A into 10 raised to power B. So the base we have selected is 10, the base of the decimal number system. So A into 10 raised to power B, where A, for example, is given in this example, the value of A is minus 5.7429 and value of B is minus 3. So if we select this particular example, then we can understand this scientific notation. The decimal point is visible. So on the left of decimal point we have minus 5, and that is called coefficient. And on the right of the decimal we have 7429 is called mantissa. And the minus 3, which is the power of 10 raised to power minus 3, the exponent is called exponent. The base is 10. So in this particular example, coefficient is minus 5, mantissa is 7429, base is 10, exponent is minus 3. But in this unit system, you have to follow the rule that base would always be 10, exponent is a non-zero integer. You can't write 10 raised to power 0 because 10 raised to power 0 is 1, identity, which is multiplicative identity. So exponent should be a non-zero integer. It can be positive or it can be negative integer, but it cannot be 0. And absolute value of coefficient. So coefficient in the example is minus 5 and its absolute value will be plus 5. Absolute value of coefficient should be always less than 10, and therefore it will involve only one digit, and greater than or equal to 1. So as a coefficient we can have 1, 2, 3, 4, 5, 6, 7, 8 and 9 only. And the mantissa will be, the number of digits in the mantissa will depend upon how many significant digits are associated in the measurement, the particular measurement. But what are significant digits and what the importance of measurement, how measurements are carried out, the topics like resolution, the topic like the precision, accuracy and error in measurements we will be taking up shortly. Now, to conclude today's lecture, I would also like to mention that the length or any quantity which has dimension of length can be assigned a value, and the modulus of that value, in some cases it may have sign also. So modulus of that value can be what? The modulus of that value can be anything between 0 to infinity in Newtonian theoretical frameworks. So all values are allowed from 0 to infinity, or modulus values are allowed from 0 to infinity. But in actual universe, in our universe, these theories, Newtonian theories, are not correct and valid theories. We have modern theories, quantum mechanical theories and the Big Bang theory of cosmology, quantum uncertainty principle and the gravitation as described in GTR plays very important role. And we now knows that we cannot measure or can through any manner the distance which is less than what is called Planck length, and that is forbidden by uncertainty principle and is 10 raised to power 1.616 into 10 raised to power minus 35 meter. So the smallest value is Planck length, and the biggest value which can be measured in any scientific experiment as on today is the size of the universe. So diameter of the universe is 880 yotometer. That is the biggest value, and the smallest value is the Planck length, and between the Planck length and diameter of the universe we can have the values of measurement of length, different examples having different length involved. But there is an idea also which is becoming popular, and that is multi-world or multiverse, and there may be many universes. And when we say universe, we mean a physically connected universe in which our assumptions of science would work, that the cause and effect, and we will come to that serious topic later. I conclude my presentation on length as a physical quantity, for time being. The measurement of length is pending, but we have introduced and realized certain issues related to the physical quantity specification in SI unit system, and we have chosen length as an example. So I end my presentation with a quote about length. The length of a man's outspread arms is equal to his height. So said Leonardo da Vinci, the great man. So you can check whether it is true approximately in your case or not. So that's an exercise given to you. In the next talk, we will be talking about time and mass as physical quantities. That will be part 3 of kinematics in one dimension. I hope you are liking my video lectures. I would like to try to improve it. I have already noticed certain problems. I would fix it in coming days of time when I have appropriate technological solution available. But if you wish to go through the video lecture series, please subscribe my YouTube channel. Please click the bell icon so that you get notification, and you may also click the like button, and you can send me the feedback also on my email address ashok.nagawat@gmail.com. So with this we conclude today's discussion. Good day.